Good morning, everyone. My name is Alex Acero. I'm a research manager at Microsoft Research, and it's a pleasure to be here today. I am going to be talking about audio and video research that has gone into Kinect. So as you can tell, Kinect has been a device that has been added to the Xbox 360 that makes gaming differently because now you are the controller. You no longer need to hold a device has all these buttons and knobs, but rather you don't even have to hold a Wii style remote. Just move your body and talk as you normally would. And that has revolutionized gaming. So it's been a very successful. So you can tell if you haven't played with the Kinect that it's a lot of fun and it's attracting people that have never played video games before. It happened to be also the fastest selling consumer electronic device. It sold 8 million copies in the first 60 days, so quite a successful device. So now you may be interested in knowing more about how it works. So let's talk about the Kinect Sensor. The Kinect Sensor, if we take the cover, is basically this set of components. And we have here the infrared projector that you may have seen, that is this device here that shines a red light. Here we have an RGB camera, standard RGB camera, and it's an infrared camera. And what this is used is in conjunction with the infrared projector to sense depth, as we will see shown soon. In addition, it has 4 microphones that are kind of here. They're underneath, you cannot see them. A motor, and it's connected by USB. And for $150, that's part of the reason why it's revolutionized the industry. So now that I've described this, I'm going to be talking about how Kinect has been using for PCs, not just for video game consoles, but for PCs as well. And then I'll go in more detail talking about the audio processing that goes into Kinect, how the depth sensor works, how skeletal tracking works and how that is important for gaming and other purposes, and head pose and facial expression tracking as well. So Kinect Hacks is a website that got started a week after the Kinect device was for sale. And what the academic and the hobbyist community was trying to do is saying, well, can we build things other than games with the Kinect sensor? And the imagination just went loose. I checked yesterday and there were like 62 pages of Kinect Hacks, which were things that the academic and hobby community did using the Kinect sensor for things other than games. It's quite impressive. There was a quote saying that every few hours new applications are emerging, and it's just a new tool that allows lots of applications that we initially hadn't. So this is a short video that shows some of the new things that you could do with this device besides gaming.
We started with a sensor that turned voice and movement into magic.
Xbox, play.
And we thought, this will be fun to play with. And it was. But something amazing is happening. The world is starting to imagine things we hadn't even thought of. Unexpected things. Helpful things. Beautiful things. Inspired things. Which is why, even though the world keeps asking us what we'll do with Kinect next, we're just as excited to ask the world the same thing.
So this is just a vision video of the things that we've seen the developer community try to do. Now let me show you what a company in Spain has done recently with the Kinect that got one of the prizes.
We have several fields of interest in our company. Some of them are related to hardware, to embedded platforms, embedded computing, but the one we have won the contest with is one related to healthcare. This is where we have been working with Microsoft Kinect.
When I received the Kinect, I was told to study the device, to take advantage of the different technology, allowing the user to use the different applications and programs in a natural way. Our main intention was to try to provide to the doctors a first version of the product in order to get their feedback.
We are now working in this voice application because the doctors want to use it. But till now, what they are trying is using the gestures. It's situated inside the operating room. In this way, they can avoid potential bacterial infections.
It's amazing to have a product, to have a device that integrates 3D camera, VGA camera, microphones.
Because of the quality of the technology, real-time performance was something incredible when you are talking about 3D.
I think that Microsoft is doing a wonderful thing with providing all the developing community with this technology.
One great thing of Kinect is that you have a lot of things inside this small package.
We hope that this system will be installed in the different operating theaters.
It's kind of cool for the doctors to use this kind of technology where they don't have to touch anything.
We are going to integrate technology in our life in a simple way.
What we have seen is only the beginning.
So if you're interested in playing with the Kinect SDK, you can go to this URL here, www.kinectforwindows.org, and download the SDK and start building some of these applications. So now that I hope that if you were not aware about the Kinect technology, you are excited, let me tell you what went inside there. And let's start with audio processing. Again, let's recap what voice control can do in this setup. And the idea is that you don't need to look for your remote control, find out whether it's on the coffee table. If you're sitting on it, if you cannot find it, just use your voice. So the advantage of speech recognition, it's complementary to gestures. Not only can you move your hands around, but sometimes it's good to talk instead. You want to do both. There is a game called Kinectimals where it's totally natural for the kids to talk to the animals. Sometimes you want to select things in a screen, but you don't want to devote real estate, part of the screen, to the buttons, such as like in the movie. You want to take the TV to use the whole screen without having devoted space to buttons that you can use with your gestures. And you want to say Xbox pause or play using the whole screen. It makes more sense. It's also very useful for accessing long lists. Imagine if you are searching for programs, there's like a large list of programs. You cannot show them all on the screen. You want to do a search, and that's where speech recognition is helpful. But one of the problems that we had when we first started this project is that a lot of the speech recognition work that has been done is using either a headset, close-talking microphone, or using speech recognition in your phone where the microphone is fairly close to your mouth. But here, the developers of the Kinect product came to us in MSR 3 years ago and said, well, we want to do this, but guess what? We want to have the microphones far away from the user, maybe 3 meters away. So, that's gonna pick up a lot of background noise and it's going to make the recognition not work. Well, unfortunately, that's not it, they told us. You have to do this when people are listening to the sound of a movie, or perhaps playing a game that is emitting loud sounds, you're shooting people. Wow, that's even harder. And that's not it. You have noise and reverberation in the room that you need to combat. The dog is running around, the baby's crying, it still needs to work. So it seems like an impossible thing, but I have a few mavericks in my team that decided to go and take a crack at it. So this is what the audio stack looks like. So we have here the loudspeakers, and there are 4 microphones in the Kinect device. So we need to do multi-channel acoustic echo cancellation, which I will describe a little bit later, and a microphone array followed by acoustic echo suppression and noise suppression. And that's the Kinect device. In addition, there's some more processing that is done in the console for audio playback, the codec for voice chat, the speech recognition, the voice interface, and other things. So let me talk first about the microphone array and the multi-channel echo cancellation. That's what I'm going to describe in this today. So the acoustical design first. The microphones are not equal space. The 4 microphones, if you think about it, this is right in the middle of this one, and this one is right in the middle of these 2. So it's non-equal spacing, and the goal is to cover the entire bandwidth. Like the bandwidth is somehow proportional to the distance between the microphones. So by making non-equal, we can cover the whole spectrum, yet not use as many microphones as we need. The other aspect is the directionality, the directivity pattern of each microphone. This is one of the things where it's a little bit of art. Ivan Tashev, who was the person that mostly developed this, had to play not just with the microphone capsule itself, but also with the rubber boot around the plastic of the enclosure of the microphone. That all makes a big difference in what the directivity pattern is. And there was a lot of experimentation done in order to have a directivity pattern that makes the microphone look forward and not to the sides or backward, because that means that it will capture much less noise. To be able to remove or cancel the signal X of T that you're playing out. That's the mono acoustic echo canceller. And if you've been using a hands-free phone, which you probably have, you've been using a mono acoustic echo canceller, which works reasonably well when you're close enough to the microphone, maybe like half a meter away perhaps. If you go more than a meter, it tends to fall apart for a number of reasons, including the fact that the filter is more complicated, it's longer, and it's harder to adapt. But mono is something that, it's been going on for a while. Now the question is, when you're playing a movie or you're playing a video game, you don't have mono, you have stereo, or you have 5.1 Dolby surround system. There was some notes that Sondi and others at Bell Labs back in 95 said that stereo acoustic cancellation has a non-uniqueness problem that presents a fundamental limitation. Essentially, it's that there are too many unknowns and too few equations to be able to estimate the 2 filters that you need to be able to extend the mono to this solution. So instead, what we decided to do is a solution where there were 2 fixed filters that were calibrated and a single filter that were adaptive. And these 2 filters meant that it was trying to see the difference between what one microphone, one speaker produces and the other one, but the rest of the room response was supposed to be captured here. So what we did is we played a calibration tone that helped us learn the basic differences between these 2 filters. That's why you need to do calibration in Kinect. And we only had to adapt a single filter. That's why we made this possible. So this is the sound that we played through the speakers for calibration. Which, although it seems like a normal melody, it turns out that it contains all the possible range of frequencies that we want the system to adapt. The first time that Ivan developed this, he had some sweeps, tones, and white noise. And our product guys said, well, you're not planning to ship that, are you? So he had to come up with, look at lots of different sound clips to evaluate the ones for which the calibration would work well. And once you do that, he managed to see that the multi-channel echo cancellation reduced 15 to 20 dB echo, which overall the entire audio pipeline was about 35 decibels. So the next stage was the microphone array processing, which had an adaptive beamformer that acts as a steerable directional microphone. So you can see it here. This is the angle between minus 150 and 150. And for this degree, this angle, which is maybe about minus 10 degrees, it puts a null. It attenuates this because it thinks there is, like here, an interference source that wants to cancel. At the same time, at about 10 or 15 degrees, it notices that that's the desired signal. So it amplifies this. This is the desired signal. So this reduces 3 to 6 dB noise on average and can suppress interference sources as well. In addition, there is spatial filtering, which means that there is sound source localization per frequency bin. This is the frequency from 0 to 8,000 Hertz, and suppresses sounds outside the desired range. And this adds another 6 to 20 dB of noise suppression. In addition to that, there is end-to-end optimization. Oftentimes, you have a cascade of processing blocks, and each one is suppressing some amount of noise. But once you put them together end-to-end, there may be interferences between one module and the next one. So what we had is every block had a number of parameters or knobs that we optimized jointly to essentially maximize the perceptual evaluation of sound quality of PESC, which correlates well with what we call mean opinion score, which is the metric that is used in designing all the speech codecs. The goal is that you present audio samples that go through this audio pipeline, to a number of subjects, and they have to rate the acoustic quality of each one of them. So PESC here is a software module that approximates with what like a lot of users would describe as the quality, but we can run this in our lab. So we have 25 parameters for optimization, including time constants and thresholds, so on. And we run a large job in a cluster that evaluated and tuned all these parameters for highest PESC and speech recognition. So here what we see this curve is a word error rate as a function of the loudspeaker volume, because the acoustic echo cancellator is not perfect. And if you don't do anything, you can see that at 100 dB SPL, you get an error rate of 65% error rate, which is unusable, of course. Even for the lower quiet conditions, is very bad. But if we put all of the modules that I described before, you can get this, which is much better. After we optimize jointly, you can get this. And once we retrain the system with this audio pipeline, retraining is a big thing for speech recognition so that it operates under match condition, you can see that the error rate is much reduced to the point that we believe is within the usable range. So I hope that that gives you an idea of how the audio processing in Kinect works and how we can do hands-free speech recognition at a distance of 3 to 4 meters, and it works reasonably well. So I'm going to shift gears and talk now about the depth sensor. So one of the things that we want is to be able to capture gestures and recognize whether someone is shaking a hand or kicking a ball and transmit that information to the game. So there are several technologies that have been developed. Here we have something by Vicon, which is what it's used in a lot of the Hollywood movie industry. For example, the movie Avatar was done this way. It's a special suit that has these sensors that you can see here, which look like little ping pong balls, that when captured, they can reproduce, we can do a mapping of what the position, the 3D capture of the person. Of course, this is something that is okay for Hollywood movies, but it's not okay for a regular user. Other types of technology have special sensors embedded in this special suit. But again, these are, although they are very accurate and high frame rate, they're expensive, they require calibration, large space, so impractical for a gaming scenario that we were looking. So what we use is what we call a depth camera, which is also a structured infrared light. This is what it's projected by that IR sensor. This is the RGB camera and this is the IR sensor. And what this is done with the IR receiver is sensing depth, so that the darker tones mean that the pixel there is closer to the sensor, and when it's lighter means that it's further away. This is cheap, fast, and quite accurate, although it has mixed pixels and shadows. So how does that work? Essentially, this projector, let's assume for now that it emits a pattern that is consisting of stripes like this. When the light bounces on a surface that is not flat like this, it's captured by the IR sensor and produces an image of this sort. So in this case, this stripe, if this was perfectly flat, it would be captured as a stripe, but because it's not, it will be captured as a different shape. So it's using triangulation to figure out under what geometry had that been such that it's captured this way. And that's how we can map this and this into depth for that particular pixel. In fact, what it is not a set of lines, but rather a pseudo-random pattern like this that gets reflected into here. So we have the IR projector, the IR camera, and a pseudo-random pattern. It's not random, it's pseudo-random. The camera knows exactly what this signal was. So then you do this correlation or triangulation, and you can find the depth. You can also overlay the depth math on an IR image to give you an idea of what this is that it's being, You can see the hands when they get closer or the head to the screen, they are darker or lighter because it's further away. And this is what the Kinect sensor is doing. And this is what a depth camera is roughly. You can see the top view and the side view as well. So obviously you can see that this depth estimation is much more accurate than RGB. Here you can see the lines could fool you, but to a depth camera it's not going to fool you. RGB only works well with light. In background clutter, it doesn't really work well. The scale is unknown, but the depth works well in very low light. And in fact, many of the customers are using this in their movie theater with the lights turned off. And the person pops out from the background. It works well for different textures. It's just much more robust. So now I'm going to tell you about skeletal tracking, which is a key component in some of the games that you've seen before. What we want to do is estimate the human pose. So we have here a human, and it has a number of joints here. And what we want to estimate is the position of these joints over time. And we can describe this with 3D coordinate space for each one of them and all the angles. And Kinect tracks 20 body joints in real time. It is hard, as you can tell, because just because you can sense depth, that doesn't mean you can sense all the joints, right? There are people of all kinds of sizes, so it's not easy. And a lot of our customers are having pets, things in their living room, kids running around. So it is not still, even though the depth camera makes things easier, it's still a simple thing. So the way we operate this is we start with the depth image, as I showed you before. The next step is to infer different body parts represented here with different colors. And then we infer the body joints where they are. And this is what we call the skeleton 3D view. So let's see how this happens. Here you see on the left the depth image. And on the right, we see not just the depth image, but the inferred body parts. That's the first part of the algorithm, what we call the body part recognition. So let's see how this works. Essentially, what we do is we classify a pixel. Like we see this pixel here, center here. We take a window of pixels around that. and we say, well, we label this as a hand. So someone went by manually and marked this region as a hand. So for each pixel in this region, we label it as a hand. That's the label. The input are just the pixels. And then we have the window, and we build a classifier. And we learn this classifier from training data. That's basically how we learn that this is a hand, or this is an elbow, or the head. And there are many possible classifiers. We choose to use a decision tree classifier here. Essentially what it is that an image window centered at pixel I, we ask questions such as, is this function larger than some threshold? If the answer is yes, go here. And then the classification is this or that. If it is no, go here, ask other questions. So the questions that we're asking until we see whether the label is correct or incorrect. And we stop the label when to, for instance, distinguish the left and the right sides of the body or things like this. So it's a matter of asking questions and comparing with thresholds and computing some statistics on those pixels and then seeing if the classification is correct or wrong. So we start here with the input depth, or here that is even when the person is occluding some of the body parts. And we label, here are like the correct ground truth. And then we see how much we're inferring. And when we have depth 1, we can only see 2 body parts. Depth 2, depth 3, we can see more body parts. 4, 5. And as we are adding depth 6, we are starting to see that the 2 sides match better. 7, 8. And as we are adding more depth to the trees, we are starting to get more accurate. And now you can see that although this still doesn't match this here, it's a lot closer. And this is what our decision tree classifier can do. And as you can see, it works well even when there's occlusions. So here we see the classification accuracy as a function of the depth of the tree. The input, the ground truth, and the body part estimation with how many trees we can add if we add more than one. So once we have the first step, which is the body part recognition, we want to find the body joints, hypothesize the body joints. And this is how the algorithm does it. We see at the top the depth image, and underneath both the body parts and the overlaid joint hypothesis that the algorithm tracks. And this is even without doing any smoothing or tracking. So the last part I'm going to talk about is the head pose and facial expression tracking. This is something that we call Avatar Kinect that a group of my colleagues developed and was shipped a few months ago. So let me show you what it does. But basically what it's trying to do is, unlike the skeletal tracking that is tracking body parts except for your head, this aspect of the program is trying to track the head itself and the pose. Where are you looking at? And also what facial gestures are you doing? Are you smiling? Are you raising your eyebrows? Are you laughing? Are you frowning? And transmitting this remotely so that you could animate one avatar in one side of the world and reproduce the movements of that avatar in the other. Let me show you how that looks like.
1, 2, 3, 4.
Ready for the big game?
Bring it on. All right, guys. 5 minutes to kickoff. Let's hear your predictions. Go.
Tigers by 2 touchdowns.
No way, guys. The Ducks are gonna run all over you.
In your dreams, the Ducks are going down.
Hey guys, welcome back.
Hey, everybody.
So I loved tonight's episode. What did you guys think?
5 stars. Heather rocks.
Ditto. She's the only reason I watch the show.
Too much drama. 2 stars.
Tough crowd. Facebook fans, what do you think?
So how does that work? So what we had here is a model that is called linear deformable model that has different faces and different gestures and different gazes. So this is a parameterization here of the, like if I have these parameters Q, I can reproduce, animate my deformable model to produce any of these expressions. And it's composed of three aspects of it. One is a standard one that depends on the base face of the person that you're trying to show, the avatar, in a neutral form. The next one has to do with the pose. Where is the face looking at? The orientation. And it has a matrix that determines the transformation that you need to do given a set of parameters. And the other part is the facial expression. For a given pose, you're looking, say, front facing. Are you smiling? Are you opening your mouth this way or that way? So what we can do is estimate the parameters A or B and all the other parameters so that we can animate this face model. So the first thing that we need to do is to estimate the parameters. And the way we do this is through an analysis by synthesis approach, where we start with some parameters here and try to see if we match the face that we're observing. And then those are the parameters that we transmit to the other end to animate the avatar. And we iterate until it converges. So when we start here, we start with a face. For a single frame, this is what the depth image looks like. After we smooth this with more frames, it looks like more like what you see of the 3D image. And then we add the texture here. So now we've converted one to the other where we can reproduce this based on this model. So now what we need to do is trying to estimate the parameters of the transformation that we saw before from both the depth image and the RGB image. And the way it works is we have the input. The first thing is we run it through a face detection, then face alignment where we identify all these points, and then we initialize our model. We try to match these points to our model here, and we do the iteration until it converges so that we estimate all of the matrices that I mentioned before. So in summary, Kinect, we think, has revolutionized gaming. This is something that we didn't expect when we started. The product group approached us because they had talked to many consultants and they all heard the same story. You can't do this. This gesture recognition is not going to happen. This voice recognition at far distances is not going to work. So it came to us and has been a great opportunity for Microsoft Research. Out of the researchers that have been working in computer vision, in microphone array processing, speech recognition for many, many years, were ecstatic to be able to work with this product group. And it surprised us. We even didn't know that it was going to be received this well, but it was a lot of fun working with them. And indeed, it has revolutionized gaming because now you see a lot of friends that didn't play games before. They were not hardcore games that like to shoot things, but now they're doing exercising, they're dancing, and it's a lot of fun. It's really revolutionized gaming. But not just gaming. We've been also surprised of the kind of things that you could do that you were possible to do before. It was just very, very expensive and not available to everyone. But when you put in a package that is $150 for the hardware and all the software comes there, and it can do not just the skeleton, the depth tracking, but also the audio, beamforming, echo cancellation, microphone array, speech recognition, skeletal tracking, pose tracking. Now you put all these tools in the hands of users and developers and academic researchers, and they can do lots of things that have really surprised us. Voice and gestures are natural for users. That means that, on the other hand, it's a lot of work for us to be able to capture it properly. Very hard to get right. But this is just the beginning, and I hope that there's a lot of work ahead and you can help us improve the technology. Thank you very much.